So I'll be talking about the topic for today, thermoset injection molding analysis and material testing. Okay, so let's jump straight into the contents for today. So to start, we will have a quick overview of the thermoset material. And then we'll be talking about all the necessary material properties and how we can do material characterization for all of them. And then after we know the material itself, we'll take a look at the thermoset injection molding simulation in our software Moldex3D, together with a successful story from one of our users. And finally, we'll come up with a conclusion to sum up the day. Okay, so now let's start with a quick overview of thermoset. As we all know, plastic polymer are categorized into two main categories, thermoplastics and thermosets. They are both widely used in the plastic industry in a lot of different applications like the automobile industry, aerospace industry, medical field, and a lot of different fields. So for thermoplastic, commonly we see in a PP, PC, PA, ABS, a lot of them, in some polymer blends. For example, PC and ABS. Sometimes we can see PC and ABS in our suitcase when we travel. Okay, and then we have another category, the thermoset, including polyurethane, PU, silicone, liquid silicone rubber, and just rubber, a lot of different epoxy, etc. So these are thermoset materials. And the main difference between thermoplastic and thermoset materials is for thermoset, a chemical reaction will take place which will create a crosslink between the polymer chains, as you can see on the bottom right. So the original material, the molecular chains, they are all separated. Once the chemical reaction has taken place, there will be cross-link between all the polymer chains that connect them all together. And this cross-linking reaction, also called curing or conversion, all the same, it is a irreversible one-time process. So originally at a lower temperature, let's say room temperature, the plastic itself, the polymer, has a lower viscosity. It's at a liquid stage. But after the material is being heated up, the cross-linking, the chemical reaction will take place, and the polymer will be hardened and enter a solid stage. And once it's entered a solid stage, it cannot return to its original status, which is why thermoset material is very difficult to recycle and to be reused for a recycled product. So due to this reason, a simulation for thermoset injection molding and actually also for other molding type, as long as we use thermoset material, simulation becomes a very valuable tool to save a lot of cost. Okay, but the advantage of thermoset material is that comparing to thermoplastic, it has a much, generally speaking, it has a smaller part shrinkage. So it's actually easier to control the part dimension. And with a lower viscosity, although flash is often observed after injection, but it's actually easier to completely fill the cavity with thermoset material sometimes. So thermoset material is still widely used in a lot of different fields. For example, IC packaging. We often use thermoset for the tire, silicon and O-rings over here, and in a lot of automobile part, we use thermoset material like rubber for sealing. So thermoset material is widely used nowadays, and with more demand, with higher demand, at the same time means higher demand for a proper and accurate and fast simulation tool for such this kind of injection molding process. So in order to finish a simulation for thermoset injection molding, we need to know what are the material properties that will influence our molding process. And with that knowledge, we'll be able to consider all those properties in a simulation. Which is why the next part we will be talking about the material characterization. First, let's take a look at our own lab in our own company, Cortec. We have a laboratory with all these equipments. Actually, right now we have even more, but we just list some of them. For example, the real graph RG25 for viscosity, and also the CR6000 for PVT. We have a PVT 6000 for thermoplastic, and for thermoset we have one machine from UChem that we can test the PVT curve for thermoset material. We have MCR 502 to measure the viscoelastic, and also it can also be used for viscosity measurement. And DSC, we can measure the curing kinetic. The Instron, we can perform a tensile test for the mechanical property. Okay, so now let's take a look at the detail for all the material testing procedures. But here I just want to show you that we have all the equipments that makes us capable of running a full material testing for all types of material. Okay, so for the plastic injection stage, during the filling stage, the curing and viscosity are the two of the most important properties that will influence our filling pattern, because higher the curing, the conversion rate is, that means higher the viscosity will be. And with a higher viscosity, it will be more difficult for filling, and later on it will influence our injection pressure, or if we're using a transfer molding process, then it will influence the transfer pressure. So curing and viscosity properties are two of the most important properties during the filling stage. So for curing kinetics, we can use the DSC 8500 with a procedure ASTM E1269. We will perform the test under 4 different heating rate from 10 to 20, 40, and 60 degrees Celsius per minute. And we'll heat up the material from 30 degrees to 250 degrees Celsius. So let's go to the next page first to look what exactly it looks like. So we'll have a heat flux plate, and at the same time record not just the temperature change, but also the heat flow. So as you can see on this graph, the beginning stage of the heating, the material will, the temperature of the polymer will increase, and under a constant heat flow. But once the material starts to be cured, so as you can see on this line, this means the curing has started. Once curing starts, the heat flow will decrease as the chemical reaction is taking place. And as you can see, after the temperature increase and the conversion rate start to increase, and when the conversion is finished, the polymer is being fully cured, then our heat flow will get back to its stable state, and then the material will keep being heated up under a constant heat flow. So this range is the curing range, and with this curve, we will be able to obtain the curing kinetic for one heating rate. So go back to the previous page. You'll see with 4 different heating rate, we will be able to obtain 4 different curing kinetic curves. And with 4 different curves, we'll be able to build the curing kinetic models. Now, from these 4 different curves, we can tell that actually faster the heating rate is, higher the heating rate is, curing will occur at a higher temperature, and also the whole curing range, temperature range, will be wider. And if we heat up the polymer under a slower speed, the curing will start at a lower temperature, and it will be finished also at a lower temperature, and the whole range is actually smaller comparing to a fast heating rate. So this is actually important for us to determine the proper temperature for our polymer, and also our mold base temperature. So now that we know the curing kinetic, the next important thing is the viscosity, the reactive viscosity. We can use the MCR 502, and under the procedure ASTM D4440, we will test the polymer with a 9 separate measurement, and pretty similar to curing kinetic, we will run the measurement at 4 different heating rate, for different thermal ramp rate under a certain constant angular frequency. So what it looks like is we'll use a known amount of EMC solid disk at a certain diameter. We'll place it in between 2 parallel plates of a rail meter, and we'll fix the angular speed of the disk under a linear temperature increase, so that the heating rate is the same, remains the same, and we will record the strain, the temperature versus time, and then we'll get the 4 different viscosity curve, as you can see from here. So 4 different curves from 4 different heating rate. And with that, we'll be able to build the whole viscosity model. Okay, so those are the important properties for filling stage. And then when we go to the curing stage, we have to consider the PVT. So pretty much like a thermoplastic during the packing stage, the PVT curve basically dominant the whole process. For curing stage, PVT for curing is one of the most important property that we need to consider. So we'll use the PT6800 machine from UCAN. to measure the PVT. So very similar to the way we measure PVT for thermoplastic. Polymer will be put in the chamber, and the area of the chamber remains the same. Only the height of the polymer will change. So under a constant pressure, we will keep a constant temperature change, so constant heating rate, and we record the height change. With the height change, we'll be able to know the volume change, and with the volume change, we will be able to know the PVT curve under the certain pressure. So we just need to test it under several different pressure, and we will be able to obtain the whole PVT model for the material. And then during the cooling stage, the thermal property becomes very important. So we'll be able to test the heat capacity and also the thermal conductivity. So for heat capacity, we also use DSC 8500 under the procedure ASTM E1269. So a already cured material will be heated up from 30 to 250 degrees Celsius with also a constant heating rate, and then we will record the whole heat flow, and by that we'll be able to know the heat capacity, the heat that is actually absorbed by a certain amount of material, and get the heat capacity property. As for thermal conductivity, we use the RG25 under a procedure ASTM D5930. The polymer will be put in this chamber, and with a line source probe, we'll insert it into the molten polymer, and then apply a certain voltage to the probe, and then record the whole temperature gradient as shown here. With the temperature gradient, with the temperature range from room temperature to 350 degrees Celsius, we will be able to test, we'll be able to measure and obtain the thermal conductivity of the material. And with this temperature range, actually we can handle basically all of the thermoset materials. And finally, after curing, after the part is being ejected, we will need to know the deformation of the part, and that is when the mechanical properties become very important. Not just the PVT, we have to know the mechanical properties, so we can test the mechanical property of thermoset material, including tensile modulus, Poisson ratio, shear modulus, and CLT, the coefficient of linear thermal expansion. The way we test it is tensile modulus and Poisson ratio will be obtained by a tensile test. We will use the instrument machine with a tensile bar. We perform the tensile test, record the whole stress and strain curve. With the stress strain curve, we will know the tensile modulus and the Poisson ratio. As for thermal expansion, we use the TMA to record, to measure a already cured material, measure its thermal expansion under a certain temperature difference. Once we get the tensile modulus and the CLT, we will be able to use these two values and calculate the shear modulus by this simple equation. So with all these measurement tests, we can obtain all the necessary material properties that are critical for a injection molding simulation. So now that we know what material properties we need to use for simulation, and we know that we are capable of running a full material characterization, we can have a look at the thermoset injection molding simulation in Moldex3D. Okay, so Moldex3D, we use a true 3D mold filling analysis, so we can calculate the curing rate of the thermoset material, and we can predict the flow pattern, can predict everything in the curing stage, and also the cooling and warpage. So with our simulation, we will be able to predict the potential weld line and air trap and all other surface defect location. And during the curing stage, we can predict the conversion rate, so users can determine a proper curing time. And based on that, we'll calculate the injection pressure, and if we're using transfer molding, then the transfer pressure can also be predicted. So a lot of the information can be provided by our simulation. And as you can see on the bottom right, this is our friendly user interface, Moldex3D Studio. It's a ribbon style structure, so it's very similar to Microsoft Office. So actually it's very easy for users to get familiar with our interface. And on the left, we have a tree structure, very similar to a lot of the CAD software. So users can easily manage all the calculation and easily manage the model, etc. And also, of course, our simulation result has proven to be very accurate based on a very large base of users with tens of thousands of simulation done every year. And it has proven that our simulation result has a very high accuracy. So in our pre-processing, we have customized material properties for users to define it by themselves. In the next page, we'll take a look at the details, and then we have an easy to use process wizard, as you can see on the bottom left. Users can easily set up the filling time, packing time, or curing time, and also the pressure profile and the flow rate profile, the temperature for your polymer and for the mold base. And users can even use a machine interface, so they can set up the whole process condition with the actual machine interface as in reality, no matter you're using Arberg machine or other brand. You can find the machines in our database and set up the process condition with the actual machine interface. Now let's take a look at the friendly user-defined material parameters. So, as I mentioned before, our own lab has the ability to test all the material properties, but if our users are able to test the material by themselves, or they are able to get the material data from the material supplier, for example, then they can actually create a material, a user-defined material by themselves in the user bank, or they can send us the raw data, and we will be able to create a customized material file for all our users. And so users can define their own material properties, including the viscosity models, the curing kinetics, the PVT curve, and others like the thermal and mechanical properties. So in these pages, I just want to show you that our pre-processing tools are actually very friendly, user-friendly, and it gives our users a lot of space to do a lot of customized things. And also our meshing kernel is all true 3D and automatic. So it's the whole pre-processing is very easy and fast. As for the result, after a full analysis, users can look at the filling, curing, cooling, and the deformation, warpage. So during the filling stage, users can easily look at the filling pattern based on this melt front time animation. You can tell how the cavity is being filled by the polymer and whether there will be any short shot that occurred. And with the accurate prediction of a filling pattern, we can give users an accurate prediction of possible weld line and air trap. So in the next page, I would like to show you the weld line locations. So as in the filling animation, the melt front actually comes from here, and the other side come from the right to the left, and two melt front will meet with each other exactly in the middle on the bottom, and this is where you will have a visible weld line exactly in the middle. So with the weld line prediction, our users can tell whether there will be any visible weld line on the appearance that can be seen on the outside of the part, and which is not that desirable for all the customers. And also not just the appearance problem. Also, weld line can influence the mechanical strength. So this is also something important, and we can actually export this result and use it in the structural analysis to determine whether the mechanical strength is strong enough in the weld line location. And then at the end of the filling region, normally we will have some possible air trap locations, so we will mark it for the users. So that means the users can be extra careful, cautious when they design the venting location. Probably they will need to put a venting location around the air trap region, so there won't be any short shot for the actual part. And then one of the most important result for thermoset material is the conversion, the curing rate. During the filling stage, if we have a very high conversion rate, if the part is being filled at a very slow speed, maybe we might have some higher curing conversion rate, and that means we'll have a higher viscosity. With a higher viscosity, we'll have a higher injection pressure, and sometimes in some very thin region, we might even have short shot if the viscosity is too high. On the for the curing stage, on the other hand, we would like to check whether the conversion rate is high enough. If at the end of curing, the conversion rate is still too low, that means the part is simply not hardened enough. So without enough cross-linking, the mechanical strength won't be high enough, and the part will not be ready for ejection. So with a low conversion, that means the users might need to increase their curing time. So this result helps users to determine a proper curing time, which can save a lot of our production cycle time, and which equals to our production cost. Okay, and after ejection, the most important thing is the deformation. So Moldex3D warpage calculation consider not just the thermal properties and the PVT of the material, also the mechanical properties altogether, and calculate the deformation of the part. And like I mentioned before, for Thermoset, normally the volumetric shrinkage is smaller comparing to thermoplastic. So sometimes it is difficult to tell whether the part is shrinking evenly or actually there's any bending or even twisting. So in our result, as you can see on the animation, we can scale the warpage to 10 times or even 20, 30 times. So we can, like shown here, we scale the deformation 10 times. So we can easily tell whether the part is shrinking evenly or it's actually shrinking with some bending happening. Okay. And then after the warpage calculation, we can also export the deformed model and in STL file. So we can use the deformed model in let's say structural analysis, or we can check whether the deformed model is suitable for is able to assemble with other assembly parts. Okay, so now that we know most of the, let's say, key features of Moldex3D results, I would like to show you one successful case from our user TYC Brother Industry. So this is their one of their part with problem during production. It's a BMC reflector with a dimension shown here, and what's worth noticing is the thickness range from 2.5 millimeter to 14 millimeter, and that actually caused some problem in some region. So here is the region that they observe some problem, air trap. So as you, if we take a closer look, you can see there are some air trap on this surface and also on this corner and this edge. It's right on the surface. And even after electroplating, the electroplating layer cannot cover this air trap, so it is actually visible on the outside. So their first target, let's say minimum requirement, is to move the air trap to other region so that there is no visible air trap on the appearance side. And if possible, they would like to achieve their final goal, which is to eliminate all the air trap so that there's no air trap at all in this part. But at least they expect to have a part without any visible defects on the appearance side. So this is the material they used for simulation, a BMC material that is already included in our public material database. Okay, so the initial results with their initial design and process. If we take a closer look to this trouble point, as you can see from the melt front, actually the melt flow through the whole bottom region first and create a closed area over here. So we have a completely closed air trap in this region, which makes it almost, let's say, almost impossible for air to escape from this region if there's no venting over here, which can be very difficult to design. And also from the ISO contour, we can tell here we have some possible weld line. So simply by this melt front animation, we can tell we might have a lot of surface defects in this small geometry, in this small region. and it is actually observed in the real part. And I would like to show you first the final results. After modification, they were able to change the melt front, the whole filling pattern, so that in this region, the melt doesn't cover the bottom part first and create any closed air trap on the top, but actually it flows from the right side to the left side. So as you can see from the animation, there's absolutely no closed air trap, no closed region that is created during this filling stage in this geometry, and which allows all the air to be able to escape from this region. So here are the modification that TYC has done. First, they modified their runner design. They add one more gate on this side so that the melt can flow from the right to the left side. And also on the bottom of this small geometry on the other side, originally this is what it looks like. And they cut out this part and this part to make the thickness more even. So as we can see in the dimension page, the part dimension is actually range from 2.5 millimeter to 14 millimeter. So actually in this small region, originally there was some thickness difference. And with this modification, the thickness becomes more even, so that the melt will not fill the bottom region first and create a closed loop on top. Once they change this part thickness, the part will be able to flow through the whole region evenly from the right to left. So after the first modification, they were with the part thickness modification. Already they are able to achieve their first target. There is, if we look at the melt front, there's actually no air trap region on top, and the melt actually meet on the bottom right side, which means there will be no weld line on top and no air trap on the top appearance side. And after they change both the runner and the part design, this is the final result they get. And as you can see, there will be absolutely no air trap on this small geometry after the modification. So then they do the tool modification, and this is the trial shot result. And as we mentioned before, with a low viscosity, flash can easily observed in thermoset injection molding. And if we look close to this small geometry, the final part, there's absolutely no air trap on this small geometry, and the part is successfully filled with very good surface quality. So TYC, they were able to solve their real life production issue by our Moldex3D simulation. So now let's go to the summary for today. Moldex3D is a true 3D simulation tool to analyze a thermoset injection molding process, and all the polymer like saturated polyester, PU, LSR, or simply just rubber and epoxy molding compounds, they can all be used in our simulation. And all the necessary material properties like curing kinetics, reactive viscosity, PVT, and other thermal and mechanical properties, they will be considered in the simulation, and our own lab has the ability to run a full material characterization for our users. And our accurate simulation result can help our users to investigate all the potential defects during the filling and curing stage, so they can optimize their part and runner design and also the process setting. And we're also capable of simulating the part deformation, the fiber orientation, the multi-component process, and basically 99% of the commonly seen issues in real-life injection molding. Okay, so this is our session for today, and thank you for your attention.